including, most importantly tonight, a clinician family kickball game. So we hope that you all have your sneakers and are ready to have some fun on the baseball field. Our heartfelt gratitude goes out to our conference planning committee this year. They came together throughout the year to discuss topic ideas, engage in advocacy, share with the community about upcoming expert series, and helped us to get to today. So please make sure to connect with Alex Alser, Sharika Rogers, Christy Abrams, Ali Hamed, Kim Yetzi, Kay Kelly, Angie Cox, Becky Nothsinger, and Megan Dominguez throughout the weekend. We also would like to thank our volunteers, clinicians, speakers, and sponsors. Without you, this conference wouldn't be possible. A special thank you to Dr. Pritchard and Dr. Ames from the University of Michigan for being our local planning team. And a very special thank you to Dr. Jerry Vockley, Dr. Melanie Gillingham, and Dr. Georgianne Arnold and Keith McIntyre. Your expertise, dedication, and collaboration are the bedrock of this conference. Throughout the weekend, I encourage you to immerse yourself in the wealth of knowledge and experiences available. Our goal at MitoAction is to continue evolving and enhancing the ways we support the FEOD community. We are committed to fostering a sense of unity and actively listening to your needs and feedback. Please don't hesitate to connect with our MitoAction team members, myself, Emily, where are you? There's Emily, and Stephanie, and we are here to learn from you and to ensure we meet the unique needs of you and your families. I hope this weekend inspires you, strengthens your connections, and reinforces the knowledge that you are not alone on this journey. Together we are stronger, and together we will continue to make strides in supporting the FEOD community. So welcome back to my families here at Detroit Country Day, and let's make this a memorable and impactful weekend. So before we begin, just a few announcements. Breaks are scheduled more frequently this year. Official snack breaks are 15 minutes. The other breaks are 5 to 10 minutes between sessions so you can quickly stretch, gather your thoughts, and check in with your children. We understand how important food and hydration are to our community, so our goal is to keep the snack and hydration table stocked so you have access to nutrition throughout the event. Please note that we have a fat-free snack table this year, and our low-fat items are by the coffee and the teas. If you have any questions about food or need assistance, please don't hesitate to ask one of the team members. Tonight, immediately following dinner, we will have a kickball game, and we encourage everyone to join us on the baseball field, which is just behind the auditorium. We'll have popsicles, music, and lots of laughs. If you have a mobility device, please find a member of the MitoAction team, and we can help direct you how to get out to the field. Bathrooms are in the Shaw lobby, which is where all of the round tables are, where we'll be having lunch and breakfast. There is a quiet room available in the auditorium green room, which is just out this door to the right, and you'll just walk to the very end of the hallway. So if you just need a space to take a break, have some quiet time, we encourage you to use that space. Dinner will be all meals will be in the Shaw lobby. Dinner tonight will be at 6:30. Tomorrow, we will take our group photo at the end of the day, so make sure you wear your t-shirts tomorrow. Tomorrow morning, breakfast will begin promptly at 8 o'clock. Make sure you visit our sponsors in the lobby. We have several new sponsors this year, including Natera, Protocol, Solace, and Nutritia, and of course, our annual presenting sponsor, Ultragenics. If you haven't signed up for the My Mito app, please make sure to see a member of the MitoAction team to get started. It's an incredible way to track your journey, to track your fat count, to track your liquid intakes, and all of the data that's provided. We have a partnership with the CPATH Institute, and we provide all of that de-identified data to researchers and clinicians as they're looking to develop new therapies and treatments for FEODs and mitochondrial disease. Children, we have a special space just for our 4-year-olds this year with activities. And if you're a parent of a 4-year-old or younger and are looking for a space to take a break, we encourage you to check out the pre-K room, which is out this door to the left. It's the second room down the hallway, and there's all kinds of fun games and activities for you to do with your child. If you are a teen or tween, we have several tables with games for you to enjoy. You'll be doing a knife cutting session and lots of fun activities. The teens are going to be in the black box, which is right out this door, straight down the hallway. And then the kids K through 8 are right across the hallway here, and we have some really great Country Day students who are in there playing with them and keeping them occupied so parents can focus on the session. And just a reminder, if your kids are going into the room across the hall, only a parent can sign them out of that room. A sibling cannot sign them out of that room for safety. All right, so let's get started. Our first session, Understanding All FAODs, is led by Dr. Georgianne Arnold. This session came to life thanks to some great questions asked by the teens last year during the clinicians panel. They are trying to make sense of how their FAOD was similar or different from the new friends they'd met at the conference. And Dr. Arnold came to us and said, I think we need to do a session next year that better explains the different FAODs, so here we are. That moment says so much about who Dr. Arnold is, not just as a clinician, but as a person. She listens first, she cares deeply, and then she educates. Over the years, I've watched her take the time to connect with families, ask thoughtful questions, and offer support in ways that truly matter. She's also joined us several times for our monthly Mito Expert series, and always focused on making sure patients and caregivers have access to reliable, understandable information. Her passion and dedication truly shine through in everything that she does. Please join me in welcoming Dr. Georgianne Arnold.
Thank you for that lovely introduction. So, maybe I'm not doing this right. Do I need to be doing anything to make my slides come up? Well. So I will just start talking. Are you in the booth trying to load them? Yes. Okay, all right. It's hard to know how to put such a talk together when there's probably variable levels of chemistry knowledge and biochemistry knowledge in the audience. So if I'm talking down to you, I apologize. If I needed to make it even simpler, I apologize, but I will be here for the next conference, so you can stop me and ask me questions anytime you have them. I don't bite. But I might not be able to talk.
Remember Steve Goodman, Shadow Puppets.
I'm sorry, I didn't hear that.
Remember Steve Goodman, Shadow Puppets.
Oh, yeah. Dr. Buckley can help me. Okay. They're having technical difficulties. So I can just start a few questions. Who here is affiliated or associated with CPT-1? CACT? CPT-2? Okay, couple. VLCAD? MCAD? Good. SCAD? Yeah, slap me for saying that. LCHAD, or trifunctional protein? Okay. GA2? Okay, good. So we've got a mix of pretty much everything here. And I know high school biology and chemistry was a while ago for some people. Well, while we're waiting, does anybody have questions that you hope I'll address in my talk? Yes? I can't hear you. Oh, okay. Well, we will talk about that in the talk. But they have many similarities and a few differences, so. Yes? Yeah, we're gonna have to get these out because I can't hear.
Is this working? Okay.
Okay, we'll get the question quick and then we'll.
Should we take the questions? If I jump through slides?
You wanna see if I answer it?
Okay. I know some of our young friends all have different fat gram limits per day, and they were asking why all their friends with different FODs have different limits.
I'm sorry, I still can't hear.
Let me start.
Okay, all right. So when I start to give a talk about biochemical pathways, people think it's gonna look like this, and they panic and their eyes glaze over. But it's really not so bad. You don't have to feel this way anymore. So let me tell you why I love biochemistry. I love biochemistry because if you strip everything down to the basics, it makes perfect sense. So I hope by the end of this talk, you will agree with me. And if not, you should come find me later and we'll talk more. So where does your body get energy from? Protein and carbohydrates give you about 4 calories per gram, but fat gives you about 9 calories per gram. So you get more than twice the bang for the buck of energy out of fat. So that's why fat metabolism is so important. So the process of making energy from fat is a multi-step process, and different fatty acid oxidation disorders happen at different steps in the pathway. So how do metabolic defects hurt you? Well, one way is what we call intoxication, that something's building up in your body that shouldn't be built up. So in the case of fatty acid oxidation defects, it is the intermediates of fat metabolism. So a picture's worth 1,000 words. When you block that pathway to making energy, things behind it build up, and they build up to a level that they shouldn't be there, and they can be toxic. So I think of it like a dam. So there was this nice river, and you blocked it up, and behind it, you're going to build up a lake of water that should have been going down the stream and is now blocked. Boy, this thing's fussy. Okay, so the other way, and probably even more important with fatty acid oxidation defects, are deficiency of the things that should have been downstream. So in this case, energy. So if you block the pathway, you block your ability to make energy. Reduced energy production is a big problem. So again, you have your nice river, and you should have had water flowing out, and you've dammed it up, you're not getting much out at the end. So how does your body use energy? Right after you eat, you are using the fuels that you just consumed. And then you digest them, they're used up for the next 4 to 8 hours, depends a little on the age of the patient. You're working off something about sugar that's been stored in your liver and to some extent in your muscle called glycogen. Now, little babies have little livers, they eat every few hours. Adults go, 6 to 8 hours between meals. So your ability to use your stores, and your stores improve as you get older, but eventually you run out of glycogen. And then you have to metabolize fat, and your body will make sugar. So the process of making sugar is glucose, neogenesis, creation. So gluconeogenesis is the process of creating sugar. And that, for fatty acid oxidation, is a big problem. Because it turns out that the energy your body uses to make sugar comes from fatty acid oxidation. So with FAOD defects, you get a double whammy. Not only can you not metabolize fat well, you don't make sugar well. And so really, once you've used up your stores, you're in trouble. So what is fat? Fat is a hydrocarbon. It's like gasoline. Your body is kind of like an internal combustion engine. So it's rows of carbon atoms with hydrogens on them. And then at the end, there's this group in the orange box that makes it an acid. So when your body is getting the message, send out the fat stores, we're out of gas, that's what your body will release. And so that's called a fatty acid because of that group in the orange box. Now the fats are named for how many carbons they have on them and whether they're fully saturated with hydrogens or not. And in this case, it's a 16 carbon fat, palmitic acid. So most of the carbons that we use, most of the fats that we use for energy are up to about 18 carbons. So the fats are grouped by long chain, 12 to 18 carbons, medium chain, 6 to 10 carbons, and short chain, 4 to 6. So the summary so far, fat's the primary source of energy, especially after about 8 hours or so after a meal, and shorter for young children. The energy made from fat metabolism is necessary to make glucose, and fats can be grouped based on the number of carbons in the fat as long chain, medium chain, or short chain. So how does a fat get metabolized for energy? So this is a picture of a mitochondria. The red is the outer mitochondrial membrane, the dark yellow is the inner mitochondrial membrane, and the white in the middle is the matrix where all the magic happens. So imagine that you're a mitochondria, you could hang out a welcome mat that says, if you're a short or medium chain fat, come on in. If you're a long chain fat, you must be accompanied by an adult, i.e. a carnitine chaperone at all times. So the first set of FAOD disorders are based on getting the long chain fat into the mitochondria. Short and medium chain fats can go in on their own. Long chains must have a carrier. That carrier is carnitine. So another word about words. Up on the top, you see the fatty acid you see in the orange box. That's the acid. In order for a fat to be metabolized, it has to be activated. And you activate it by adding something called CoA, or coenzyme A. Where does CoA come from? You make CoA in your body. And one of the things you use it next time you take a vitamin, look at the bottle, is pantothenic acid. And so your body has to make the CoA and put it on the fat. Now that fat is active, it's ready to be metabolized. But if it's a long-chain fat, it has to first be attached to carnitine. So fatty acid is on top. A fatty acyl-CoA is the fat that's activated with the CoA on it. And a fatty acyl-carnitine is the fat that's attached to carnitine. So when we throw those words around, you'll know what they mean. So all fatty acids have to be activated by esterifying or attaching to CoA, but the long chain get a carnitine attached to them using CPT1, the enzyme CPT1. So I'm not really going to talk here about carnitine transporter problems. I'm really going to just talk about CPT1. So carnitine and the acyl-CoA, that's the fat with the CoA on it, through CPT1 get turned into an acyl-carnitine now, and the CoA gets booted off. So in this picture, the bubble membrane is the cell membrane, and the thick orange membrane is the outer mitochondrial membrane. So this is happening in the outer part of the mitochondrial membrane. There we go. Then you have to get that acylcarnitine through the inner mitochondrial membrane. And you do that with the enzyme CACT, or carnitine acylcarnitine translocase. And again, a picture's worth 1,000 words. The gray is the inner mitochondrial membrane. So CACT takes the acylcarnitine through into the inner mitochondrial membrane. Whoops. I'm trying to go backwards, but it's not working. There we go. All right. Then the final step is the CPT2, carnitine palmitoyltransferase type 2, takes the carnitine off. So now you have an activated acylcarnitine that's inside the matrix of the mitochondria where it's all ready to be metabolized. And if you had a short and a medium chain fat, you don't need to do all of that. So we went through CPT1 that hooked the carnitine on, CACT that pulled that acylcarnitine, the fat with the carnitine, into the matrix through the inner mitochondrial membrane. And then CPT2 takes that carnitine off, puts the CoA back on, and you basically have another acyl-CoA that's ready to be metabolized. So you went through all of those 3 steps just to get the fat inside. Now you're ready to make energy out of it. So CPT1 and 2 deficiencies have variable severity. They can be neonatal lethal, they can be adult onset muscle disease, they can be anything in between. So if you're looking at one person who has CPT deficiency 1 or 2, and you want to know why they don't look like you, we'll talk a little bit about that later, but basically they can really vary. CACT deficiency is typically pretty severe. Again, probably somebody will stop me later and say, well, I know a case that isn't. But most of the cases I've seen have been pretty severe. So each cycle of turning that activated acyl-CoA into energy is a 4-step process. At the end of the 4 steps, you'll take 2 carbons off the fat. Those 2 carbons can be converted directly to energy, and the energy goes into the electron transport chain, or it could be turned into ketones, and the ketones are sent out to other organs in the body so that they can get energy in your brain, in your heart, and in other places as well. Okay, so the first step of the 4-step cycle is a dehydrogenase, a dehydrogenase. Now, I told you biochemistry is not that complicated, and a dehydrogenase takes away hydrogen. Yes, see? So there are three main dehydrogenase enzymes that work on the acyl-CoA. There's very long chain, there's medium chain, and short chain. And then there's GA2, where none of your dehydrogenases work. Oh, well, I can't click on it. I had a sound effect here. But wait a minute. I said long chain, but that name is very long chain. How did that happen? I didn't hear that. So it turned out the enzyme, they thought they had the LCAD enzyme. And then they discovered they were wrong. The LCAD enzyme did something else. So when they found the correct enzyme, they named it VLCAD. However, it is a source of confusion because we talked about the mitochondria where your body breaks down the 18 to 0 carbon fats. But there's a separate system in the body that breaks down fats that are in the range of the 20s, 20, 22, 24, 26. And that happens not in the mitochondria, but in a different part of the cell. And they're also called very long-chain fatty acids. So if you decide to go home and read about this, just make sure that you're working in the right system, the mitochondrial fatty acid oxidation system of long-chain fat. So a picture's worth 1,000 words. The first step is the acyl-CoA dehydrogenase. And so you have your acyl-CoA. The R just stands for more carbon atoms. So it's not specifically telling you exactly how many fats were there because it just makes it easier to show the picture. So you have your acyl-CoA. It goes through the dehydrogenase enzyme. And if you look on the far side, you'll see that a hydrogen's been taken away from the second carbon. Now, carbon always makes 4 bonds, so that means that those 2 carbons are now going to double bond to each other. The second step is a hydratase. And what do you think a hydratase does? It adds water. It adds water across that double bond. And so the word OH is biochemical shorthand for hydroxy. And it goes on the 3rd carbon, and I'm going to explain to you what that means. Next. So if you look down on the right-hand side, you can see that you've taken a water molecule, you've hydrated this, you've added it, and the second carbon in now has 2 hydrogens again, and the other OH from the H2O that's water now attached to the 3rd carbon. So you've put in oxygen on the 3rd carbon. Now, one of the ways, some biochemist someplace decided that number names weren't good enough. He wanted them to have, the carbons to have letter names too. But he didn't give carbon 1 a letter name because he didn't think anything important ever happened to that carbon. So it starts with the second carbon in. The second carbon in is the alpha carbon. Remember the Greek alphabet? Alpha, beta, gamma, delta. The 3rd carbon in is the beta carbon. So what you have done is oxidize the beta carbon. And that's why the process of breaking down fat for energy is known as beta oxidation. See, when you strip biochemistry down, it isn't hard. Next slide. Oh, I'm sorry, go back. So now you have a carbon with a hydroxy group, the OH, that's on the 3rd carbon. So this is 3-hydroxy, or also could be called beta-hydroxy acyl-CoA. Next up, next slide. So now there's another dehydrogenase enzyme, and because it works on the dehydrogenase with the hydroxy group on the 3rd carbon, it's called 3-hydroxy acyl-CoA dehydrogenase. Now, getting into what Dr. Gillingham talked about, some people have a problem with the it's called CHAD, L-CHAD, so long-chain hydroxy-acyl-CoA dehydrogenase. You put that H in there for hydroxy. Some people have a problem with just the L-CHAD enzyme. It also turns out that the L-CHAD enzyme is held on a protein with steps 2 and 4. So steps 2, 3, and 4 of this process are on a protein called the trifunctional protein. Trifunctional because it has 3 steps on it. So some people have a problem with the trifunctional protein, and some people have a problem with the L-CHAD protein. They're fairly, in many ways, similar in presentation, but there are some unique details to each one. Next slide. So this is the picture of the 3rd step. And what you have done is taken away a hydrogen, and you took it away from the 3rd carbon. So now you just have that C double bond O. And then, go on. The last step is called a thiolase, and basically it cleaves off right before the 3rd or the beta carbon 2 carbons, and that 2 carbon piece can be metabolized. And so you go through this 4-step cycle to take off 2 carbons, then you go through another 4-step cycle and take off 2. So if you start with, let's say, a 14 carbon fat, after this it's 12, you do it again, now it's 10. And when you get down between 12 and 10, you switch enzyme systems from the VLCAD enzyme to the MCAD enzyme. And then when you get down to 6 carbons, you switch over to the short chain enzyme system. And you keep going down till the fat's metabolized. Next slide. So this is your picture where you broke off this 2 carbon piece, acetyl-CoA, and then you're back where you started from, except now your fat is 2 carbons shorter. And these have long names, but if you just remember the dehydrogenases, you're doing fine. Next slide. So this is a picture. And there's no pointer here, is there? This is a picture, so you start up in the left corner with the long-chain fatty acids, and then you activate it by putting the CoA on it, and now up at the top in the brown box, you have long-chain acyl-CoA. Through CPT1, at the outer mitochondrial membrane, you combine it with carnitine, and you make a long-chain acylcarnitine. The long-chain acylcarnitine, using CACT, passes it through the inner mitochondrial membrane into the matrix where all the magic's happening. And then CPT2 takes the carnitine off and leaves you with an intramitochondrial long-chain acyl-CoA. Then you go through the 4 steps of beta oxidation, and if you're starting with the long-chain fat, it's the VLCAD, and then the long-chain hydratase, LCEH, and then the L-CHAD enzyme, and then the long-chain thiolase, the LCCAT. In the meantime, this beta oxidation is feeding electrons into the electron transport chain. So that's what GA2 is. So people with GA2 deficiency have a defect in all of their dehydrogenases, not just VLCAD, not just MCAD, not just SCAD, and a dehydrogenase that breaks down something called glutaric acid. And that was discovered because when they found people who had elevations of glutaric acid, some of them had one kind of disease and some had another. So this other disease got called GA2, and it's a disease not only of metabolizing glutaric acid, it's the gluteryl-CoA dehydrogenase that doesn't work. But all of their fatty acid oxidation dehydrogenases don't work either. Then you can feed that acetyl-CoA into the Krebs cycle or TCA cycle, or you can make a ketone out of it and ship that ketone out to important places in your body for energy. Next slide. So I want to say a word about the word acylcarnitine. Carnitine's main role in life is to hook on to or esterify to long-chain fat to pull it into the mitochondria. But carnitine is quite fickle. It will attach to anything that looks like fat. So if you think back to the dam, the block in the pathway where you're building up the lake of intermediates behind it, partially metabolized fats, carnitine is going to hook onto all of that. So that can cause two things. One is it can deplete your carnitine, and so anybody who survives a fatty acid oxidation defect has to have even a little bit of enzyme activity. And so now you can't even do that. You can't even get that in because you've deprived yourself of carnitine. And also, those acylcarnitines building up in that lake behind the dam can be toxic. So carnitine is both a curse and a blessing. Next slide. So what are some of the things that are common to fatty acid oxidation defects in general? Variable severity and variable age of onset, fasting intolerance, hypoglycemia, and we talked about why any of those occur. Next slide. But I want to say more about the variable severity part and the variable age of onset. Next slide. So we say that enzymes fit with a lock and key metabolism. So the blue lock is the enzyme, the brown key, orange key is the substrate or the fat. Next slide. So the enzyme lock and key model is that your fatty acyl-CoA fits into a very specific slot in the enzyme. Once it's bound in there, the magic happens, the chemical reaction takes place, and out comes your shorter fat and your 2-carbon piece if it's a fat enzyme. So the shape of that enzyme is really important. Next slide. So this is actually a picture of the MCAT enzyme. And all those curly loops are just different amino acids in the protein. And the purple is where the medium chain fat is binding in there. And it turns out that the enzyme doesn't just work alone, 4 of them glom together. So you can see it makes what we call a tetramer of 4 of the MCAD proteins together, and then you can see the purple medium chain fat that's sitting in there, which is where the chemical reaction takes place. So if you change a really important part of the protein where that purple enzyme sits, you're going to have a lot more trouble. So if you make a minor change, if it turns one amino acid into a similar amino acid, the key might have to jiggle a while before it works in the lock, but it'll work, and so you might have milder symptoms. If you really severely change the shape of that place where the key fits in, it's not going to work at all. So there's the difference in severity can be due to the difference in what the change is in the gene that makes the enzyme protein. Next slide. Also, genes have stop signs. When your body's reading a gene, it has a start here sign, keep reading, and a stop here sign. If your change in your DNA inserts a stop sign too early, then you won't make the whole protein. So what are some of the things that affect your severity is what that DNA change does. Does it introduce a stop sign too early? Does it change the shape of the protein so that the enzyme can't even, so that the fat can't even fit into that slot that it should? Or does it change some other part of the protein that doesn't really make a big change in the slot where the fat goes in? And that can be a more mild change. And sometimes it's hard to predict. So if you have a new change, if your newborn screen comes back and they find a new change in one of these enzymes, they have to predict, is this a child who's going to have severe disease and we should put them on this low-fat diet and do all these things for them, or is this somebody that we can kind of just watch, take care of when they're sick and catabolic, but maybe they're not going to be sick as neonates. So when the labs that sequence the genes will put it through computer modeling programs and help us kind of predict. I mean, if it introduces an early stop sign, we kind of know. But sometimes it's hard to tell, and sometimes the computer modeling programs don't agree. So there may be one or two of you out there who have a case where they're kind of just watching and seeing how severe it's going to be. But this is why when you look at two people with the same enzyme problem, two people with VLCAD, two people with CPT2, there can be a lot of difference in how severely affected they are and what their age of onset is. Next slide. So this is the VLCAD enzyme activity. You can see somebody with two completely working genes has 100% enzyme activity. Their parents, who are carriers, have 50% enzyme activity and are asymptomatic. But then as your enzyme activity gets lower and lower, you get more and more symptomatic. So on average, babies with cardiomyopathy with VLCAD tend to have an average of maybe like 6%. People who get an older adult onset muscle disease, maybe their average is maybe like 34%. Unfortunately, I'm sure Dr. Vockley will tell you, it's measuring enzyme activity is fraught with issues, including one laboratorian who said to me, sometimes it depends on how much coffee I had that morning, how much substrate I'm putting into the assay. So we don't necessarily just do enzyme activity on everybody. Next. I think it's mostly done as a research basis. Is that correct, Jerry?
We're trying to move it to clinical.
Pardon me?
We're trying to move it to clinical.
They're trying to move it to clinical. Okay. So what's unique and common to long-chain disorders? Your heart loves ketones. Your heart really, really, really loves ketones. And if you don't feed it any ketones, it will not be happy. So the long-chain fat disorders that affect your ability to make ketones, if it's severe enough, can present with cardiomyopathy. And we used to think it only happened in babies. We now know that is no longer true. You can have, many of them have rhabdomyolysis, muscle problems, and then some neuropathy and the retinal problems when you get into the L-CHAD and the trifunctional protein. Next slide. So, do I have time? Yes. Oh, no. Well, I'm 2 minutes over. We started late. Should I do the treatment? Okay. So, how do you treat MCAD? Well, fasting prevention is a big deal. Mostly patients do well on a heart-healthy diet. Now, you got to realize in America, a heart-healthy diet is probably a fat restriction because, a bacon double cheeseburger, fries, and a chocolate shake is a common American meal, but it is not a heart-healthy meal. I did have one patient once with MCAD who actually needed a feeding tube and really couldn't go more than a few hours without eating when she was a baby. And we all thought, well, she can't have MCAD. But when we got the ability to do gene deletion studies, we discovered she had a severe mutation on one gene and the other gene was completely deleted. It wasn't there at all. I actually moved away when she was 5 or 6, but they found me for her high school graduation and invited me. And I had that chance to go, which was wonderful. And she had been in the track team. She'd learned how to manage her disease. She'd learned how to eat during practice to keep her energy levels up. She had a crop top on. It was a hot summer day. She had a little scar where her feeding tube had come out. And so there's even severity differences in MCAD. The use of carnitine is controversial. When I was first training, everybody went on carnitine. Now, it kind of depends on the clinic you're in. Some will monitor you for deficiency, some won't. Again, your deficiency further decreases your ability to metabolize the long-chain fats, but on the other hand, you're building up the potentially toxic intermediates. So I won't tell you how your clinic will manage you. Next slide. For long-chain disorders, certainly fasting prevention. Some patients need significant fat restriction. Some need not so much fat restriction. Most patients, if you remember, you're getting twice the bang for the buck out of metabolizing fat. So if you have a long-chain fat disorder, if you feed somebody medium-chain fat, that can enter the mitochondria without needing carnitine, and it bypasses the long-chain enzyme, and you can get more energy out of medium-chain fat. So you can see why medium-chain supplements are really important to people with long-chain fat disorders. And again, carnitine supplements are controversial. We don't really want you to be deficient, but we want to make sure that you're not building up excessive intermediates. And so clinics vary in how they prescribe that. Next slide. So in summary, fatty acid oxidations can occur from defects getting long-chain fat into the mitochondria, that's CPT1, CACT, and 2, or in the four-step oxidation cycle in the dehydrogenase enzyme, VLCAD, MCAD, and SCAD, and the 3-hydroxydehydrogenase, which is where LCHAD and TFP, or when all the dehydrogenases don't work well, which is GA2. And the severity and age of onset can be variable. Next slide. Fat's a very important source of energy during fasting, and fatty acid oxidation disorders lead to energy deficiency, the buildup of potentially toxic acylcarnitines, and decreased ability to make glucose. Next. And so hopefully I haven't blown your minds with all the biochemistry. And if it didn't make perfect sense to you, find me later and we'll go through it again. Okay, thank you. Oh, there'll be questions.
Are there any questions? Did she answer the question about why you guys are different up there in the back? Does that make sense? Why some of you guys can have some more fat and some can have some less fat? Yeah. Yeah? All right. Any other questions? Oh, yeah.
Where does the carnitine go that exits off of the CPT2 part?
Say that again, please. I have hearing loss, and when I was packing, I couldn't find my hearing aids. Yeah.
She said, where does the carnitine go when it goes off the CPT2 part?
It goes back out through the inner mitochondrial membrane, out into the outer part of the mitochondrial membrane so that it can be used again by CPT1. Good question.
Anybody else? All right, thank you so much, Dr. Arnold.
All right, so I know that we're all here, and some of you guys know each other from last year, and some of you guys are new here, and sometimes it's hard to figure out what to do, how to intermingle, but we're gonna do something fun, breaking the ice FAOD style. So we are all gonna actually head to where all those tables are, and I encourage you to sit next to somebody you don't know. Okay, and this is, we're really strongly encouraging the teens to come because we need your spice and we need your flavor in the room. So if you are a teen or a tween, if you can kind of come and help us out, we're gonna do an FAOD icebreaker. And then after that, we'll have snacks and stuff available as well.